Okay, so our next section is going to be 8.2. We skipped a little bit ahead just because of the what's going to work best for what you guys have already done and what we're doing right now with not being in the classroom. So, okay. So here we go. Area between two curves. Sometimes we need to find the area of a region bounded on top by one curve and on the bottom by a second curve. We are also going to do some where it's like on the right and the left, okay, where there's bounded on the right and the left side. Right? We'll worry about that in the second video of the second installment of this week's work. Okay, so let's just take a look at this one. Okay, so find the area between the curve y equals 2x plus 1. I'm sorry, 2x squared plus 1 and this graph between 0 and 2. Okay. So in order to help me do this, I'm going to think about the graph. And so this one, it's going to have a y-intercept of 1. It's going to be opening up. It's going to be like this. Okay. For this guy here, this graph, it's going to be opening down for myself. And we'll kind of see where that graph is going to be. For us here. Let's see, well, it has a y-intercept of -6. 6. Okay. And, I mean, if I factor it, okay, I can see that I get these two, so my graph's going to look something like this. Okay, you don't need to be perfect with the graphs. You just need to kind of be able to get a general sense. So we're just going from 0 to 2, right? Because it tells me between 0 and 2. So we're just working on this region right here. Okay. So for each of this, we want to think about this. That when we do area in general, it's going to be the area of rectangles that we have. And so for this one, let me draw the rectangle. Right, let me just pick one right in the middle. Here's where my rectangle is going to be. If I just look at this rectangle, you can see it goes, its width is still dx, okay, and its height here is delta y, is the change in y. So the change in x is my width, change in y is my height. Okay, to get that change in y, I can see I go from the top function to the bottom function, right? So basically, for this one, right, to get that height, it's just how far apart they are. So the top function is the 2x squared plus 1, that's the y value there, and I'm going to subtract the lower one. So I'm just getting my difference in the y values here. As I move things around, okay, there's my function, and this is the height at any given point for myself. Okay, that's how tall this rectangle is going to be. It's just going from this function to this function. So right here, this is the upper minus the lower. So what you really need to do as you work through these problems, you just need to figure out which function's on top, which one's larger, and which one's smaller, and then you just subtract the two. Okay. What's nice is it doesn't matter if the graph is below the curve. All right. If you're like for example here, if I'm subtracting this negative y value, it's going to be like, you know, subtracting a negative is going to make it plus, and it's going to make it a bigger value there. So all the signs are going to totally work themselves out here. Okay. If I'm looking at this value, this is 2, and this was what's -6. 2 minus -6 gives us 8. That's the height of the rectangle right there. Okay. So we always do the upper minus lower. It's going to give us what we need for our height for the rectangle. Okay, so let's add up all the rectangles and just do it. Remember that this integral symbol, this elongated s, tells us to add up all the rectangles we have over the interval from 0 to 2. Okay, the height of the rectangles are 3x squared minus 5x plus 7. That's my delta y right there. And my change in the x is just an infinitely small change. That's what the dx represents. Okay, and so at this point, right, let's go find that area for me. And this doesn't, you can see the shape is kind of random, so I'm just going to do my antiderivative. So the antiderivative of 3x squared is x cubed All right, 5x squared over 2 plus 7x. Those are my antiderivatives there. Okay, and so let's evaluate that from 2 to 0. Okay, so I'll plug in 2. Now give me 8 minus 10 plus 14. So that's the upper bound. The lower bound, I plug those in, and it's going to nicely just give me zeros for all of it. So, you know, it doesn't always happen that way, but because I told you it was starting at x equals 0, right? That's why it happens. So if you see that it starts at x equals 0, it's pretty common that you get a 0 right here. Okay. Let's see. So I put these together, and I get 12. Okay. This must be positive. Let's put a little note there. Right? Must be positive. Okay? We're finding the area between the curves. It's always a positive value there. If it's negative, that means you had the wrong value, your wrong function as the upper bound, and the wrong one as the lower bound. You flip-flopped it. Okay? If you flip-flopped it, then you just go back and you change your signs, right? And that'll make it work. So you just make it, put a negative in front here, negative in front here, right? Or you can swap those bounds, and it will be just fine. Okay? So again, this must be positive because it's area between curves. It's kind of like when we were doing last week when we talked about total area. Total area also had to be positive. Okay? Okay, so let's look at example 2 here. Find the area of the region bounded by the graphs y equals x squared and y equals x cubed for the interval 0 to 1. And you can see that just like the homework, there's going to be some that give you the graph, so you don't have to know every single graph. Okay, so that's nice. We just have to figure out which one's larger and which one's smaller here. So maybe it's hard for you to figure out which one's larger. So we're just between 0 and 1. Notice the 1 right there. Okay. If I'm at 1/2 and I square it, that gives me 1/4. If I cube it, it gives me 1/8. So the bottom one is the smaller one. And the top one. So the bottom one's the cubed, right? The 1/8. So when I plug the 1/2, and the top one is the x squared, because that was a 1/4. Okay, so that's how I knew which ones they are. My rectangle's going between those two, right? Okay, the rectangle you can see is the height of it is the change in y, so the change in y is just the upper minus the lower. Upper being the x squared equation, the lower being the x cubed. So that's my change in y. Change in y is the height, right? The difference in y. My delta x is just the incremental change, so I'm going from 0 to 1. Dx, right? That's the width, and the height being x squared minus x cubed in all cases. Again, this is not a typical shape, right? We can't do this geometrically. We're going to have to do the antiderivative. Okay. And plug in my upper bounds minus the lower bound, which is 0. Nicely goes away. So I have 1/3 minus 1/12. I'm sorry, 1/3 minus 1/4. I was jumping ahead. All right. Common denominator is 12. So my answer is going to be 1/12. Okay, and you say, wow, that's super small. But if you think about it, look at the scale that we have here. Right, at 0 to 1, it still looks skinny. So it's really not much of an area. This whole thing is an area of 1 because it's 1 by 1. So you can see that doesn't. Now that makes a little bit more sense that that's 1/12. Looks like it's a very little portion of that. Okay. So let's try another example here. Find the area of the region bounded by the two curves y equals 1 and y equals sine of x. Okay, so this is another one without, excuse me, without an equation given. So we'll do what we can. We're going from 0 to pi over 2. Okay, so really all we care about is 0 to pi over 2 as we're graphing this. So the curve y equals 1, well, that's a constant, so I'll put that right there. Let's see, sine of this plug in a value. So sine of 0 is 0. And sine of pi over 2 is 1, so the curve is kind of going up like this. Even if you don't remember perfectly what the shape is, the important thing is you know that this one's the upper and this one's the lower. So here's my rectangle right here. Okay? So the height of the rectangle is the upper minus the lower. The upper being 1 and the lower being the sine of x. Okay? So in this case, it's a little bit it's a little bit different, right? It's not a polynomial here. Doesn't mean we're going to change anything. The height of the rectangle is 1 minus sine of x. The width is the dx, right? This is dx, the infinitely small width there. And we just need to know that from 0 to pi over 2. Okay? So, we take a look at this, and we say to ourselves, okay, what's the antiderivative? So, x plus cosine of x, because the derivative of cosine is negative sine. Yep, so it's a plus cosine. Yep. Okay. Bounds are 0 to pi over 2, so I'll put those in. Okay, so now let's plug in the upper bound here, and we have pi over 2. Cosine of pi over 2 is 0. Okay, let's plug in 0. Cosine of 0 is 1. So this is the case where, like, if you forget that lower bound just because it's 0, you'll get the wrong answer. So, not a polynomial, so that's why there's a value here. So let's see, we have pi over 2 minus 1. All right, so we have our answer there. Okay. So, and that's okay. No need to make a common denominator. That problem's all set.